Acids and bases 1. The essential idea. Many reactions involve the transfer of a proton from an acid to a base. Nature of science. Falsification of theories. Hydrogen cyanide altering the theory that oxygen was the element which gave a compound its acidic properties allowed for other acid-base theories to develop. Theories being superseded. One early theory of acidity derived from the sensation of a sour taste, but this has proven to be false. Public understanding of science. Outside of the arena of chemistry, decisions are sometimes referred to as acid tests or litmus tests. And theories can be supported, falsified, or replaced by new theories. Acid-base theories can be extended to a wider field of applications by considering lone pairs of electrons. Lewis theory doesn't falsify Bronsted-Lowry, but it extends it. Chemists use several theories to explain and predict the behaviour of acids and bases. The Arrhenius theory. This was one of the first theories proposed for acids and bases, and it's based upon the release of H+ ions or hydroxide ions in solution. But there are some discrepancies within this theory, and it isn't used in the IB. The Bronsted-Lowry theory, I'll say that again, the Bronsted-Lowry theory, a popular theory used to explain acids and bases, based on the transfer of hydrogen ions between reactants. The Lewis theory, which is HL only, but we'll discuss that a bit later on. It's a useful theory used to explain acids and bases, and it's based upon the transfer of electron pairs between reactants. The Bronsted-Lowry theory, based upon the transfer of hydrogen ions, protons, between reactants. Acids donate a proton to another reactant. Bases accept a proton from another reactant. Bronsted-Lowry acids, reactions with water. If we react hydrochloric acid and water, we form H3O+ and Cl-. You can see that the acid here has donated its H+ to water to form this hydronium ion. Sulfuric acid and water. Again, we can see that the sulfuric acid has donated one of its hydrogens, or in this case, both hydrogens, to two waters to form two hydronium ions. And so I bet you can guess what's going to go on here. That's right, the ethanoic acid donating its hydrogen to water to form this hydronium ion. Press pause and see if you can work out the Lewis structure of the hydronium ion, and then you should also, if you can, try and recall an alternative name for ethanoic acid, and you can scribble down another formula should you choose. Did you get this? And we can call ethanoic acid acetic acid. Some people may think you can call it vinegar, but vinegar is very diluted. I think it's got like 4% ethanoic acid in. So acetic acid is the alternative name for ethanoic acid. Vinegar is just a very dilute form of it. Bronsted-Lowry bases reactions with water. Ammonia and water is going to give us NH4+ and OH-. You can see this time that the water is donating a hydrogen ion to ammonia. Ammonia is accepting the proton. Bicarbonate ion, should I say, sorry. Once again, you can see it's accepting the hydrogen ions. And methylamine, this is accepting hydrogen ions to form the NH3+. Bronsted-Lowry acids and bases, reactions without water. We've got hydrochloric acid and ammonia. Let's see what's happening. Obviously that hydrogen in hydrochloric acid is being donated to the ammonia. So hydrochloric acid, obviously the acid, ammonia is the base. Below here we've got vinegar and baking soda. Vinegar is dilute ethanoic acid donating its proton. So obviously the baking soda is acting as the base there. Let's talk about amphiprotic species. A species that can donate and accept a proton. They act as both a Bronsted-Lowry acid or as a Bronsted-Lowry base. Water is an amphiprotic species. You can see in this top reaction here, the HCl with water. Water is accepting a proton from HCl, but it's donating a proton to ammonia. So it's acting as a base when it's with hydrochloric acid, but acting as an acid when it's with ammonia. HCO3 minus, it's accepting a proton from HCl, so it's acting as a base, but it's donating a proton to water in the second example, so it's acting as an acid. Okay, we've got here ammonia acting as both a base and an acid, so what do you think we're going to get? Well, if it's acting as a base, that means it's accepting a hydrogen, so it's going to become NH4+, and so in the other case it's going to be donating a proton. Amphoteric species. A species that behaves both as an acid and a base, but not necessarily by donating or accepting a proton. This may involve other acid-base theories. If you look at the diagram up here, you can see all amphiprotic species are indeed amphoteric. Here's some examples of amphoteric species that aren't accepting or donating protons. Here you can see aluminium hydroxide reacting with the acid, so obviously it's behaving as a base and it's forming a salt. And then this aluminium hydroxide down here is reacting with a base, so obviously it's behaving as an acid. We've got aluminium oxide too, they're reacting with an acid, so this is behaving as a base, again making a salt. And we have an example of it behaving as an acid down here, reacting with basic sodium hydroxide. We're going to look now at Bronsted-Lowry conjugate acid-base pairs. You can see here HA would be an acid and it's reacting with a base, and it's in equilibrium with a conjugate acid and a conjugate base. You can see here that HA is acting as an acid because it's donating a proton. But if we look at the other side, it's this base here, once it has the proton attached, if you're going the other way, this way, then this is acting as an acid in the reverse reaction. We call that the conjugate acid. Okay, so the base becomes a conjugate acid and the acid becomes a conjugate base because A is accepting a proton over this side. So the pair, the acid and conjugate acid, the acid and conjugate base, would be HA and A minus. It's acid and its conjugate base. And pair 2 would be the base and its conjugate acid. We've got ethanoic acid here with water, the ethanoate ion and the hydronium ion. You can see obviously this is the acid and this is the base. So if this is the acid, it becomes the conjugate base. If this is the base, it becomes the conjugate acid. If we went the other way, back this way, then obviously this is donating the proton. This has become the acid. So the base, the acid conjugate base pair, these two and these two. Here we've got ammonia and hydrochloric acid reacting. The base is obviously the ammonia and acid, obviously the hydrochloric acid. The acid donates a proton here to form NH4Cl, ammonium chloride. But if we look at the two ions, if you go back the other way, it's the ammonium ion which would donate a proton back to the chloride ion. So this has become the acid. So the base conjugate acid pair would be ammonia and ammonium, and the acid and the chloride ion for the acid conjugate base. Okay, let's have a look at this. What is the conjugate base of an acid? Well, you can fill that in. So press pause and fill both those in and see if you can find what the rule would be. Okay. Obviously, the two rules are as follows. To find the conjugate base, you just remove the hydrogen. Okay, and you put a little negative sign. So CH3COO minus, Cl minus, etc. Down here, what is the conjugate acid of a base? You're just adding H plus. NH3 goes to NH4 plus. H2O goes to H3O plus. OH minus, which go to H2O. Splendid.